Distance protection relays provide fast, selective protection for electrical power systems. The trip decision depends on the distance to the fault and provides protection as selectively as possible. If the relay detects a fault in the first part of the line, designated as Zone 1, it will trip instantaneously. If the fault is further away, subsequent zones provide an additional time delay to allow the relay in the next section of line to clear it first. These relays identify the zone in which the fault occurs by measuring the impedance of the fault loop and comparing it with the impedance represented by the zone setting. Since the impedance of the ground differs from the impedance of the conductors, the relay must apply a correction factor to determine the distance of a ground fault from the relay. This factor is usually called the K factor, the ground impedance matching factor, or the residual compensation factor, depending on the manufacturer of the relay. Until now, the K factor has been calculated from system data. This calculation is problematic if the topography of a line is complicated. Parameters such as the height of the conductors above the ground and the soil resistivity can have significant influence. For older cable installations, some of the parameters required in the calculation may simply be unknown. Due to the large number of different parameters required and the difficulty in obtaining data, the calculation can be error-prone. As an example, a large utility requested our device for measuring the parameters to calculate the K factor of a line where zone overreaches had occurred. The measurements showed that whereas the positive sequence impedance matched within a few percent, the imaginary part of the zero sequence impedance was measured with an error of 48%, 16.1 instead of 23.8 ohms. Weeks later, the reason was found. The company's database contained an incorrect DC resistance value for the ground wire used. Measurements to verify the calculation of the relay settings can prevent overreaches and are obviously a good idea. Until now, measurements to verify these calculations have rarely been performed due to the excessive effort which had been involved. CPCU1 and CPC100 make these measurements both simple and fast. The line is grounded at the far end, the CPC is connected via the CPCU1 to the overhead line to inject the current, the voltage is measured, and impedance and residual compensation factor are automatically calculated. The CPC can take measurements away from the power system frequency, hence reducing the power required to overcome interference from other substation plants. As a result, the size of the equipment is greatly reduced. The equipment is connected to the overhead line through a grounding box, which also protects the user and the equipment against unexpected events on the line. CPCU1 includes safety isolation transformers, which also condition the signals from the CPC100. The CPCU1 is connected to the grounding box. Setup is complete when the CPC100 is connected to the CPCU1. Measurements are carried out on 7 measurement loops: A to B, A to C, B to C, C to ground, A to ground, B to ground, and ABC in parallel to ground. Line impedance templates guide the user through the measurement procedure. The resulting file is loaded to a PC. In MS Excel, the K-factors can be displayed in various common formats. The costs for the K-factor measurement are small compared to risking the enormous costs of a possible power outage. To accurately detect a fault, your relay must have accurate K-factor settings. This requires precise measurements of the impedance of the line and ground return path. CPC 100, together with CPCU1, is the best tool to measure it.